Good morning, Astronomy 1020. Welcome to another exciting episode of Radiation, Light, and Matter. We're going to try something that's never really been done before in the history of Astronomy 1020. We're going to attempt to do this entire lecture without the use of iced tea. So I don't know if it's possible. We're going to find out. But I'm a little short in iced tea today, so you're going to have to bear with me. I'm going to teach you about the inverse square law, about macroscopic properties of light. I was trying to see if I could do Newton's prism demonstration for you guys. It requires a prism. Ooh, you guys, can you guys see that little rainbow there? It would actually be kind of cool if I could get the rainbow to go right into the lens of the camera. Kind of twisted it just. Normally, I got very good at doing this demonstration inside the classroom. Inside the classroom, I had a big transparency projector, which pushed light in one single direction. Normally, to perform this experiment correctly, you need to collimate the beam, okay? And collimating the beam means you're sending the light through a very thin slot, which I attempted to put in this cardboard container here. It would be much better if the slot was of uniform thickness. I cut this with a box cutter and I was doing it hastily this morning. And so once it goes through the slot, then you can adjust the prism's position until you can get a rainbow. And I sort of had it, but it wasn't perfect. I'm just looking for another box I can balance this on here. I don't want to waste the whole damn day on it, but it would be cool. I had it for a minute there, but it wasn't satisfying. It wasn't as satisfying as it normally is. Okay, that's the camera. I've got too much junk in here, guys. Let's give it one last shot. So you can see there's a slot of light there. I'm just trying to see what the camera can see. And then if I twist this, so right now the rainbow is like behind me. No, you guys can sort of see the beginning of it up over here, but unfortunately it's just too dim and my apartment is too bright. Well, I'm going to have to keep, I think having this at just the right position is a part of it. So we'll keep working on that as time goes on. I want to start off today by talking about this light bulb. If I were to ask the class, what is light? Or if you had like a kid brother who asked you what is light, what would you guys say to them? What would be your response if someone asked you what light was? I'm waiting for some big ideas here. What is light? No, we got nothing? Or Stacy?
Yeah, it's an electromagnetic wave. That's
what you would say. You'd say it's an electromagnetic wave. Exactly. And then when they said, what the hell is that? You'd say, geez, I don't know. Well, it takes a long time to learn about electric and magnetic fields. You have to take an entire class on it. We're sort of leaping over that class and getting right to the good stuff. Let's start by considering this guy right here. This is a simple incandescent light bulb. And on Tuesday, you can't hear me, Arunsak? Okay, I don't know. Anyways, when we analyzed light from the incandescent bulb, on Tuesday, what did we see? What sort of spectrum did it produce? If I take my spectroscope and I point it at a light bulb, what would you see? Hey, you know what? I realized, I don't know if I did this last time, but I could probably, instead of using the prism, I could use a diffraction grating, which is like a type of prism. I wonder if I could. Oh, there we go. So there's a whole bunch of spectrums in every direction. What kind of spectrum is that? If I, oh yeah, tripping out. So what type of spectrum does this incandescent light bulb produce? What does the spectrum look like? Yes, thank you, Kevin. Thank you very much. A continuous spectrum. It's a rainbow, right? Let's share our screen for a moment here. And let's get to our, our lecture notes. We know that when we pass white light through a prism or through a diffraction grating, we get a pure rainbow. And as Kevin reminds us, the pure rainbow seen here is what's known as the visible continuous spectrum. That's your new word for rainbow, is visible continuous spectrum. A continuous spectrum is a pure rainbow with no breaks in it. It's the sort of thing that you just saw when I held that grating up to your camera. You could see the rainbow popping off in a bunch of different directions. It turns out that there are different ways to analyze light. When light pours through a church window, like you see in my slide here, this contains zillions upon zillions of individual photons. You know that light is made up of little particles called photons. But when we deal with light in a macroscopic sense, you can't really count up all the individual photons any more than you can count up all of the atoms in a box full of air. There's just too many of them. So in the same way that we have to deal with the properties of materials differently at the large scale than at the small scale, we have different ways of talking about light and energy when we deal with a beam of light. This is a beam of light, and sometimes in optics we consider light to be made up of a whole bunch of pencil-thin rays. And each ray itself would contain zillions upon zillions of photons, but a ray is a way to sort of keep track of the direction in which light is going, okay? Here, light streams through a window. Let's start by considering a light bulb. I think I have a slide for that somewhere. Here's a light bulb like the one that you just saw me holding. It's an incandescent bulb because there's a filament in it. You're heating up that filament by sending a current of electricity through it. And as you heat up the filament, it begins to glow. When it glows, it will begin to shine light. And the light will be emitted isotropically in all directions. So anywhere I can draw a ray coming from the filaments out into space, light will be shining in all 360 directions and more because it's in 3D, okay? Suppose I wanted to measure the energy that flows from this light bulb. I'd have to capture the light coming out of it. And one way I could do that is with a kind of goofy device called an integrating sphere. Here's a picture of this device called an integrating sphere. We use this to measure the output of energy of light. So you've got a little Edison socket in here where you screw in your light bulb, and then you close up the sphere, which is light sensitive. And as the light bulb shines, you begin to read the energy output on your computer here, okay? So let me talk to you guys about a concept in physics called power. Let's take some notes. This is the bad marker. Actually, I think it's time for a fresh one. Okay, let's talk about a concept in physics called power. Power, writ large, is an amount of energy flowing through a system per unit time. It is a measure of energy flow, and it is not the same thing as energy. In the case that I just considered, I had an incandescent bulb and I plugged it into some light socket, and light began to stream out in all 360-degree directions. When an object emits light uniformly in all directions, it is called isotropic. A light bulb is not perfectly isotropic because there's a little plug here which does not shine light. But a star, a sphere that radiates light, is isotropic. I couldn't talk about measuring the energy of a bulb because once I plugged it in, energy would be continuously flowing through the glass, out of the system, into the surrounding environment. I guess to measure the entire energy the bulb could put out, I'd have to turn on the integrating sphere and leave it on until the light bulb burned out. And that's not exactly what we want. That's not helpful for us. We're interested in how much light will flow out in a day, or how much light will flow out in an hour. Or if we were to use MKS units, we'd want to measure how much energy would flow out of our system in a second. What are the MKS units of energy, students? I want to make sure I'm talking to an enlightened group here. What are the MKS units of energy? Oh, shit. See, I thought I was talking to some knowledgeable students. Austin, can you help us out? The joule, Daniel, thank you. So the MKS units of power are the joule per second, and we define a joule per second as a watt. So watts are a measurement of power, okay? We can write 1 watt is equal to 1 joule per second. Now, anything that uses energy in some unit of time can have a power associated with it. Examples could be the amount of calories you consume per day. The average human consumes somewhere between 2,000 to 2,500 calories per day. And that is a power. And you have a wattage associated with you. A guitar amplifier might use 300 watts. And that's the amount of energy flowing through it in terms of electricity. A hairdryer might use 100 watts or something like that. This light bulb here is a 40-watt appliance bulb. And that tells me once I turn it on, 40 joules are streaming out of this bulb every second. When we talk about the power associated with light, we use a slightly different term by convention. We call it the luminosity, okay? I don't know where I'm gonna write that, so I'll write that down here. Luminosity is the power of light. It uses the same units. For instance, if I said the luminosity of my bulb was 40 watts, I'm telling you the power. So I could talk about the power of a light bulb, that's fine, but usually it's customary to say luminosity of a light bulb. You would never talk about the luminosity of a hairdryer or the luminosity of a guitar amplifier. That wouldn't make sense. Once it's a system like that, you just call it power. So I'm just trying to tell you, power is the general term, but when we deal with light, we like to call it luminosity.
Is that related to like lumen?
It is related to lumens, like you mean on a projector?
So I know I've heard the term for light is like measured in lumens or something.
So it turns out that lumens are a measurement of a related quantity. And that quantity is called brightness. And that's one of my goals today, Christopher, is to help you guys understand the difference between luminosity and brightness. So can I erase some of this so I can have my board back? Are we cool? All right. Since you mentioned it, Christopher, that's something I want to do. Let's try to separate these two concepts and define them in terms of each other. So we have luminosity versus something called brightness. Luminosity is the light output in all directions from a light bulb or from a star. So for instance, if I take a light bulb and I tell you that the luminosity of the light bulb is 100 watts, I'm telling you how much radiation is coming out of it in all 360-degree directions. And an interesting thing about luminosity is luminosity is a fixed property of a glowing object. So luminosity is a fixed number, a fixed property of a star or of a light bulb. It does not depend upon distance. If I have a 100-watt light bulb, it's pumping out 100 watts whether I'm really close to it or whether I'm really far away from it. It's fixed, okay? However, you do not get to detect all of that light. Obviously, if you put your eyeball up to the light, so here's a light detector, okay? This is your eyeball, and your eyeball cannot capture all the light coming out in all directions. Your eyeball is going to capture some small cone of light, and that cone of light that you're going to capture is called the brightness, okay? So the brightness is defined as the luminosity of a bulb divided by some unit of area, and that's usually the area of your detector. Now, area here is a very general and sort of abstract term. Let me show you a little picture to help here. Is the resolution low for anyone else, Donovan asks? No? Donovan, it might be your internet connection. So stick with it as you can. And if you have trouble seeing something, just ask me about it, okay? Hopefully it'll get better. Let me just show you guys a couple of pictures here for a second. This is a great picture that kind of explains the difference between luminosity and brightness. Here you can see a bulb, and we're following one cone of light coming off of the bulb. And maybe we've designed it so that this cone contains 1 watt, okay? At a distance of 1 meter, that watt is splashed over this unit of area. This is a square meter panel. And we'd say that the brightness is 1 watt per square meter. And you'll notice that as the cone travels through space, the cone gets wider and wider and wider. And even though you still have 1 watt in this cone, that 1 watt is being spread out over a larger and larger area, so that for each little panel, the brightness, the amount of light you detect, gets dimmer, okay? Let's try a couple of examples that might help here, okay? We talked about luminosity as the light output in all directions. We talked about it being a fixed property. Let's start by considering the sun. Okay, the sun has a fixed luminosity of 4 times 10 to the 26 watts. And that's kind of like a really big number. If you wanted to compare it to something, we could say that the United States of America has a power requirement of something like 1 times 10 to the 20 joules per year. And I'd like you guys to compare the energy that the sun puts out to the amount of energy the United States uses, and that's all the states in the US for an entire year. Suppose I asked the following question to the class. Suppose I asked, in 1 second, how much energy does the sun emit? So in other words, what I'm trying to get you guys to think about is, what if I could surround the entire sun with an integrating sphere? with a solar panel bag that would collect all the light from the sun for just 1 second. In fact, we have a name for this in science fiction. In science fiction, it's known as a Dyson Sphere. A Dyson Sphere is a hypothetical concept in which humans could become so technologically advanced that they could build a humongous spherical solar panel which surrounds the sun, and then like some kind of a cosmic tick, we could just suck the energy right off of our star and use it to power all the things that we want to power with energy, like spaceships or Nintendo or something. So can you guys answer? Well, even cooler than the Death Star, because this will absorb energy from a star. Can anyone answer this question? In 1 second, how much energy does the sun emit? How do I do that? My lecture's a little janky today because I don't have my iced tea, so I need you guys to work with me here. How do I figure out how much energy the sun emits in 1 second? This is not supposed to be a hard question. It's supposed to be an easy question.
I feel like it would be the same number, because isn't like a watt like the amount of joules per second or something?
Correct, but you see, Christopher, as usual, you're thinking about numbers and I'm thinking about units. So I'm not saying you're wrong. I just want to know what the answer is. How much energy does the sun emit? What would be your answer then, Christopher?
Four times 10 to the 26 joules per second.
Right, but see, the whole thing here, Christopher, is I didn't want you to say joules per second, because joules per second is a luminosity or a power. I've asked you about just joules, says Daniel. That's right. The answer, Christopher, you kind of figured out, is in 1 second, the sun emits 4 times 10 to the 26 joules. The trick, Christopher, was to make sure you could understand the difference in the units, okay? Which I think you do now. Christopher, is that more or less than the United States uses in 1 year?
More. It looks
How
like.
much more? Okay, so let's ask another question. How long could I power? Let's not use power. That's a little bit of a charged term here. How long could I support the United States energy needs with 1 second of sunlight? And that's total sunlight in all directions. Do you know how to do that, Christopher?
I think that would mean dividing the sun's energy output by the US power consumption.
Great idea. So we'll do 4 times 10 to the 26 joules divided by 1 times 10 to the 20 joules per year. Okay, Christopher, let's start by dividing the lead digits. What do you get when you divide that by that? Christopher?
4 million.
Oh, okay, fine. So 4 divided by 1 gives you 4 times 10. 26 minus 20 gives you 6. What are my units?
Years.
Right. Joules cancels with joules. The bottom of the bottom is the top. You could supply the energy needs of the entire United States for 4 million years if you could collect just 1 second. If you could collect all the photons emitted from the sun for 1 second, in a Dyson sphere, you could power the US for the next 4 million years. That's pretty
I
wild. If you
feel
think.
like that's a really good supporting argument for solar energy.
It is. So I guess the next question, it absolutely is. You don't realize just how much energy the sun's pumping out. So Christopher, my next question, and I'm trying to give you a hint here, why don't we get to do that? How come we're not capturing all of that light?
Well, I could think of a few reasons, but I think the one related to this class would be that we can't yet at least surround the sun with an energy capturing thing.
Right. Right now, in our current state of technology, we're kind of over here on this blue dot, and we don't get to capture all of those photons because not all of the photons make it to us. Maybe this many photons from the sun make it to us here, but the rest of the light from the sun is wasted, and it travels into outer space so that aliens can see our sun twinkling like a star in their sky. All of that energy gets lost to the vacuum of space. We only capture a small fraction, a small area of that light, and that small area is what is called the brightness, okay? And let's take a look at my slide that came just before this to understand how this works. I'm going to introduce a really important formula called the inverse square law. But first, I just want to show you how it works conceptually. Let's imagine that the sun in the middle is pumping out 4 times 10 to the 26 watts. That's its luminosity. And if I surround it with a Dyson sphere that's this big, then 4 times 10 to the 26 watts will be splashed over this entire sphere. What I could then do, if I wanted to know how many watts were coming through a square meter, and by the way, guys, this is going to come up several times today. I want to, there's too much stuff. I want to give you guys a sense, a rough sense of what a square meter is, okay? A square meter is bigger than a pizza box. It's actually kind of about the size of this whiteboard here. So here's 1 meter tall by 1 meter wide. You can see that my whiteboard is pretty close to a square meter. So it's kind of like the side of a refrigerator box or something like that. Or maybe the box that your oven would have come in from the appliance store. So I just want to point out that a square meter is a pretty big unit of area, okay? So if I were to look at that picture again, I could take this first sphere and I could divide it up into a whole bunch of square panels. And if I divided 4 times 10 to the 26 watts by all of these little square meters, I would know the brightness streaming through 1 square meter. Now, if I go out to a bigger sphere, a sphere here, I'm still splashing 4 times 10 to the 26 watts across the entire sphere. But because the sphere is bigger and because its surface area is bigger, there are more square panels all over its surface. Let's try to put that into a formula up on the board. Let me introduce the inverse square law. This is one of the most important formulas in astronomy. I'm taking my time with it because we're going to use this almost every class. So in the inverse square law, the setup is I have a star with some luminosity, and the luminosity is pumping out in all directions. And I'm going to surround that star with some kind of a sphere. Now that sphere has a radius associated with it, okay? I know from basic geometry that the surface area of a sphere, this is something that you usually prove in a geometry class. The surface area of a sphere is 4 pi times its radius squared, okay? And if I want to derive the inverse square law, I would start off by saying brightness is luminosity divided over the surface area of the sphere, okay? Brightness is luminosity per unit area. And then I would plug in the formula for the surface area to derive this formula. Brightness is luminosity over 4 pi r squared. And this formula is what's known as the inverse square law. Hello? Hi. What happened? Yeah, I'm getting that, Cam. Guys, I turned around and you were gone, and this time it wasn't my power plug. Did you guys all just drop out? What was it like on your end?
You just froze.
Shit. I'm sorry, guys. It's the damned internet. Well, at least we didn't lose the recording. That's what's important. Can you guys tell me where I froze? In the slide it said, shoot, I just don't know how much you guys missed. Okay, let's try this again. Maybe the simpler version, since the pigeons are after me, I know. There are two versions of the inverse square law, okay? Let's try this a different way. There are two versions. Version 1 is that the brightness, the amount of light that you receive, is the luminosity over 4 pi times the distance squared. And version 2 of the inverse square law is that the brightness is the luminosity over 4 pi r squared. In actuality, there's only one version of the formula, but it doesn't really matter whether you use D or whether you use R. It's a luminosity divided by some kind of area. But this formula can be used in a variety of different ways. In both cases, the units of brightness are watts per square meter. And brightness very much depends upon distance, okay? And this is just as simple as a basic observation. If I were to take this 40-watt light bulb and turn it on, if I put it right up to my eyeball, the brightness that my eyeball would receive, the number of watts per square meter, would be very large, and it would probably hurt my eye and blind me. But as I move the bulb further and further from my eye, the amount of energy in that cone would get smaller and smaller and smaller, and the bulb would appear dimmer to me. It's important to realize that you detect brightness. You always detect brightness. Honestly, I think doing an example problem is the best way for us to kind of get to know these two versions of the formula, okay? So does everyone have that written down? I'm gonna start with a sample quick. Oh, okay, Caitlin needs a sec. I'll sip some water. You cool? Okay. I have to move faster here. Okay, so let's try this question. Find the brightness of the sun at 1 AU, a distance of 1 AU. In other words, let's just look at a cartoon picture here. Let's imagine we were on the International Space Station, and let's imagine that we did a spacewalk, okay? And let's just have an image. So we want to neglect the effects of our atmosphere. So let's imagine, you know, you're this guy here, and he's holding some kind of a cap there. But what if instead of a cap, what if this was a solar panel that he was holding? So he's at a distance of 1 AU from the sun. He's above the atmosphere of Earth, so we don't have to worry about that affecting the light from the sun. And we just take a square meter solar panel and we hold it directly towards the sun. How many watts per square meter will be slammed against that panel? Do you guys know how to go about this here? So let's actually draw the picture. So the picture is, here's the sun. The sun is emitting light in all directions. We're surrounding it with a sphere of 1 AU. And we're asking if we hold a solar panel up roughly at 1 AU, we want to know the number of watts per square meter that are coming through that solar panel. Where this solar panel is supposed to be 1 square meter, okay? How would I go about doing that, students? Do you want to use Formula 1 or Formula 2? You could really use either one, but.
Formula 1.
I'm sorry, you guys kind of cut off at, you said Formula
1.
Okay, I like that because I like to think of this as the distance between you and the star. So that works for me. So we have the brightness is the luminosity over 4 pi d squared. What are we going to use for our luminosity?
Four times 10 to the 26 joules.
Not joules, Caitlin. A luminosity is not measured in joules, and energy is measured in joules. Try again. 4 times 10 to the 26.
Watts? No, wait, not watts.
That luminosities are measured in watts. Now, what is the distance?
1 AU.
Okay, but I want my brightness to come out in watts per meter squared, not watts per AU squared. So what am I going to have to do?
Convert it.
I think that's a U job, Caitlin. So what is 1 AU equal to in some other unit? Do you know how many kilometers are in an AU? Bet you could look that up. These are things that I will try to provide on a formula sheet. During the exam, I'll probably have a formula sheet that looks something like this, and it'll have, well, this is for my 1010 class. It doesn't seem, oh, here we go. Right there, Caitlin.
150 times 10 to the 6 km.
Okay.
Kilometers.
150 million kilometers. But we need this in meters. So what are you going to do about that, Caitlin?
You're going to do an X bar.
Yep.
Kilometers on the bottom, meters on the top.
Yep. What's your
And
conversion
then-
factor?
1 on top. Is it 10 on bottom? I'm so sorry.
Mm. No. No one knows the number, the conversion from kilometers to meters? What if I had a formula sheet for you on the exam? Oh, Devin says 1,000 meters is 1 kilometer. A few people are chiming in. So they're helping you out there, Caitlin. Caitlin, this is very important. The 1,000 goes next to the meters, right? And the 1 goes next to the kilo. Okay? Okay, so what's my answer then? 150 times 10 to what power, Caitlin?
Three.
No, you have 6 zeros and you have 3 zeros.
9.
9. 150 billion meters is equal to 1 AU, all right?
Are you waiting for me?
I'm kind of waiting for you to write that down because I'm using up my board really fast here. Okay, let's plug it all in. the brightness at 1 AU will be 4 times 10 to the 26 watts divided by 4 times pi times 150 billion meters squared. I want to see who can plug that in. Take out your calkies, punch and crunch. I bet you screw this up. That's what I'm guessing. Everyone punch and crunch or incur my wrath. Oh, I'm taking too long on this. Sorry, Chris, not correct. Yes, Christopher, you did it good. Yes, Arunsak, you did it good. How about all those trolls hiding back there? What the hell are you guys doing anyways? You must just be smoking weed and watching TV. I have no idea what you guys are doing. I sure hope you're punching stuff into your calculator. Sorry, Caitlin, no good. Get that calky. Sorry, Blair, not 1.4.
I can't find the square button. Oh, found it.
It's at the top. Sorry, Tiffany, no good. Sorry, Caitlin. All right. Okay, I've learned what I need to know, which is you guys need some help, okay? Well, maybe Arunsak got it, but Arunsak, just bear with us here. Okay, you ready? Ready to do it like a pro? You're off by a power of 10, Austin. Okay, let's try it together. Ready? 4 exp 26 divided by 4 divided by pi divided by 150 exp9, square it, and then hit equals. Emily, let me see. Yes, Emily. I like it. Yes, Caitlin. Okay, can you guys remember that? Yes, Tiff. You've got to divide by 4, divide by pi, divide by d squared. Okay, how should I round my answer then? Now help me understand the answer. What is the answer? $1,400 watts per square meter, says Arunsak. That's exactly what I wanted to hear. Arunsak, if I have a 100-watt light bulb and I plug them into that solar panel, how many 100-watt light bulbs could I power with that solar panel?
14.
Exactly. And this number is actually a famous number in technology and engineering. This number up here has a name, and it goes by the name of the solar irradiance. The solar irradiance, I might have spelt that wrong, irradiance. The solar irradiance is the maximum amount of energy that you can get from the sun at Earth's orbit. So this is what the solar panels could grab in theory from the International Space Station. That is above our atmosphere. Guess what it turns into by the time you get down through the atmosphere? Once it hits the ground and you're grabbing solar panels from your roof or you're grabbing light from your solar panels, you get 400 watts per square meter. So you basically lose you lose 2/3 of it to your atmosphere, to scattering and absorption. Believe it or not, 400 watts per square meter is still a pretty good amount of energy. Remember that a square meter is the size of this small mini chalkboard that I have here. With 2 of them, you grab 800 watts. With 4 of them, 1600, and it goes on and on. If you cover your entire roof, in theory, as long as the sun keeps shining, you can power your house. The real issue is being able to store it in some good battery storage, which is what the company Tesla is famously working on. Better battery storage so that we can capture more light from the sun and store it more efficiently. Guys, what if I had tried to calculate the brightness at the surface of the star? Yes, Earth would be scorched. The atmosphere protects us not only from some of that general sunlight, but also the sun, it turns out, emits a lot of ultraviolet radiation, which is very, very harmful to life. Our atmosphere is a shield of sorts, okay? Okay, so you've learned the difference between brightness and luminosity. I'm going to be asking you a lot of questions about that. It's important for us to be able to calculate the brightnesses of stars, both on our sky and on our surface. Let me say one last thing about this. Can I erase? Anyone have an issue with me erasing? Okay. Before I move on, I want to say something, and this is really me trying to help you guys when it comes to the exam. For the 2 versions, here's how you use the 2 different versions. This version, brightness is L over 4 pi d squared. This is the version used to find the brightness of a star on the sky. Usually if I tell you a star has this luminosity and it's located 50 light years away, you would use this version, the version 1. Sometimes I'm going to want you to find the brightness in a different sense. Rather than finding the brightness on your sky, and let me just show you a cartoon here to help you understand what I'm talking about. This would be using it to find the brightness of a star in the sky, but sometimes instead of brightness in the sky, I might ask you to find the brightness at the surface of the star. In other words, if I went to the surface of the sun, we're going to do this in our homeworks today, and I put a 1 square meter panel right at the sun's surface, how much brightness would I get there? That's when you want to plug in the radius of the star. And that's when you use brightness is L over 4 pi r squared. And this is to find brightness at the surface of a star. And the problem is I'm going to be asking you to do both calculations from time to time. Here's the picture there. So you have a star. The star has some radius and some luminosity, and you're basically trying to find the brightness right at the surface. Whether the sphere is at the surface of the star or whether the sphere is 1 AU, it kind of doesn't matter. But at your stage of development, students at the 101 level tend to get really worked up about whether R means radius or D means distance. So I think it's probably more helpful for you guys to think of 2 different versions of the formula for 2 different applications. Okay, good. Cameron understands me. That makes me happy. We'll see more examples of that as we go forward. Okay, the next thing that I'd like to do is I'd like to talk to you guys about the way that light interacts with matter, okay? There's kind of a cool slide in your book that I think is worth looking at. I used to think it was cheesy until I realized that it could be very helpful for a new student who's learning about how light interacts with matter. And I want to show you slide 35 and just talk about it for a second. The study of light in optics is very complicated. There's lots to learn. And this little cartoon picture is attempting to show you guys the many different ways that light can interact with matter. And I think I might actually want to take this as a note, but let me just kind of walk you through with my crayon here. So let's start by considering the sun, which we were just talking about it. The sun is an emitter of light. Some things actually emit light and produce their own light. Examples would be the sun, examples could be a light bulb or a glowworm, or even these cool glowing drumsticks that I like to use when I'm making music. Okay, so these are kind of fun. So these things are emitters of light. Once light is emitted from an object like a glowing drumstick, it travels into its environment and it can interact with matter in a bunch of complicated ways. Let's see some of them. You all know that if you walked on the driveway or pavement in the middle of summertime, that you can really burn your feet just walking on blacktop, right? That tells you that the ground can absorb sunlight and absorb that energy and get warm. But the ground doesn't just absorb sunlight, it backscatters some of the light as well. And scattering is one of the principal ways in which light interacts with matter. Light can also be transmitted as if through glass. Light can be reflected as off of a mirror. There's so many different ways that we can use these terms, we should probably try to keep track of them. So let's call this interactions between light and matter. This is a little bit of an indulgence here, but I want to do it. So light can be emitted, for instance, by the sun, or by a light bulb, or by a glowworm or a lightning bolt. Light can be absorbed, okay? Light is absorbed by the ground. The ground can absorb sunlight, but individual atoms at the atomic scale. Cameron, if you want to talk about lightsabers, it's a little bit of a non-physicsy thing, but I think the idea behind a lightsaber is it's a beam of plasma. We're going to talk about plasma at some point, so let's defer that until then. But by the way, Cameron, if you're interested in this, there's a UK physicist who actually wrote a paper on the physics of lightsabers, if you want to go there. So we could talk about that, but they're mostly some made up stuff. Sometimes you have to hang up your physics hat to enjoy science fiction. So light can be absorbed by the ground and light can be absorbed by atoms. Light is usually not only absorbed, but light is also scattered. And light can be scattered also by the ground, by your clothing. Atoms, individual atoms can scatter light. One of the examples I like to use in lectures sometime is to have you guys just contemplate a red dot. Now, the discussion isn't as fun when you guys are all on the other end of a computer screen, but class, is the red dot an emitter of light? Yes or no? Arunsak says no. It's not producing its own light. So how do you see it then, Arunsak?
Whatever light is in your room is scattered off of the board. Right?
Exactly. So white light from my lamps and things and from the windows is coming towards the board. The board is scattering white light in all directions. This must be absorbing all the colors except for red. It's absorbing the green, it's absorbing the blue, but it's backscattering the red. What I think is interesting, Arunsak, is if you think about it, any place I go in my room here, I can still see that red dot, right? It doesn't disappear when I move around the room. And that means simultaneously, there must be light scattering from every piece of that dot must be scattering light to all spots in this room. So just think about how many photons have to be scattered per second for that red dot to be able to flood the entire room. In some ways, this room is being flooded with light. Mad photons, exactly, Arunsak, mad photons. Okay. Light can interact with matter in a couple of other ways as well. In addition to being scattered, light can be reflected. Reflection is different than scattering because reflection preserves the geometry of the rays. Okay, so by a mirror, Sometimes water can reflect light. The difference between scattered light and reflected light is something like this. When you have scattered light, a beam of light comes in to your dot, and then it just bounces off in every direction isotropically. That's scattering. The difference between scattering and reflecting is in reflection, light comes in at some angle, and it bounces off at the exact same angle. So you can usually see an image of whatever you're looking through in the mirror because there's a one-to-one geometry between the rays coming in and the rays coming out. This is a bit more organized than the scattering. I cannot see an image of the lamps in my room by staring at this red dot. It's scattered light, not reflected light, okay? Light can be transmitted by glass. There's many different. There's a couple of other more abstract ones that I'd like to talk about as well. Light can be refracted. The refraction of light is the bending of light as it passes through glass. Here, I might like to show you guys a picture. Do you guys see this little setup here? They have a light source, and they've collimated the beam by passing it through a very narrow slit. Oh, I like your cat, Tiffany. What's that kitty's name?
Olive.
Hey, Olive, what's up? That's a cool cat. Okay, so here comes light through a very thin collimated beam. And notice when it strikes glass, it bends and makes a little downward motion. And when it leaves the glass, it comes back in the other direction. This is a property of light called refraction. It's the bending of light when it passes through a thicker medium. As you guys have already seen, refraction doesn't just bend light, but refraction can actually separate light into its component colors because the purple light gets bent slightly more than the red light does. So that's an example of refraction right there. Light can also be bent or diffracted, and these are things I want to teach you about. So transmitted by glass. Refracted is the bending of light through glass. And diffraction is quite complicated, so I'm going to talk about that at the end of our lecture if I make good time. Learning how to use these terms correctly is learning about how light interacts with matter, okay?
Like, what's it called when light gets, like, bent from the gravity of a black hole?
So when light, it's called the deflection of starlight. Although it's complicated here because sometimes light can be bent around a star or a black hole, and sometimes light can actually be slowed down as it tries to leave a star. There are more complex terms for it called gravitational redshift. Believe it or not, Christopher, those are things that we're trying to work towards in our class. But when light is bent by the gravity of a black hole, it's actually quite similar to what happens when light gets bent through glass. And I have some friends, some astronomy professor friends, who make their careers studying something called gravitational lensing. So to answer your question, which is a cool question, Christopher, sometimes the light from distant galaxies can actually be bent by nearby galaxies, and it bends the light in exactly the same way a lens does. It's possible to create these cool structures called the Einstein ring. And I want to show you what's going on here. So here in the Einstein ring, you have a foreground galaxy. So the orange thing there is an elliptical galaxy full of trillions of stars. And somewhere behind it in the very distant universe is a galaxy that's emitting blue light, and it's probably something like a spiral galaxy. But the light from the galaxy is actually being smeared out and bent into a ring by the gravity of the nearby galaxy, and it actually functions just like a lens. In fact, it's kind of cute because sometimes there's this one famous image from gravitational lensing They call it the smiley face, where basically the gravitational lensing from background galaxy makes a little smiley in space here. So this is a sort of more advanced topic, but it is very much, that would be very much related to refraction. That's how lenses work, okay? Cool question. Okay, let's imagine that we want to break light apart into its components. That's called taking a spectrum, and that's what you did in your labs last time. Let's take a note about that. So when I take the spectrum of light, excuse me, a spectrum is when you break light apart into its component. And here I could say a number of different things that are all related to each other. I could say breaking light into its component colors. I could also say breaking light into its component wavelengths. I could talk about breaking light into its component frequencies. And I could even talk about breaking light into its component energies. And you know what, class? All four things are just different ways of talking about the same thing. So this, and this they're all the same thing. And you're supposed to kind of already know why they're the same thing. Because you learned some formulas, if I specify the wavelength of light, that tells you its color, its frequency, and its energy by these formulas. The speed of light is wavelength times frequency. The energy of light is Planck's constant times frequency. And the energy of light is Planck's constant times the speed of light divided by wavelength. These three variables, wavelength, frequency, and energy, are all related to each other by one of these letters. And that goes for the entire electromagnetic spectrum. Remember that? So let's take a look at the EM spectrum again, which I think is slide 63. Let me try this. So we could just, it's true for the visible spectrum, but here, notice that in the electromagnetic spectrum, wavelength increases to the right, right? So we sometimes refer to this as the red end of the spectrum and this as the blue end of the spectrum. So gamma rays are very short wavelength, radio waves are very long wavelength. But notice that energy, I'll use a different color like blue, energy increases not to the right, but it increases in the opposite direction. So as you go from radio waves to infrared to visible to UV to X-rays to gamma rays, the energy of the photons gets higher and higher, and the radiation becomes more dangerous to you. Radio waves pass right through your body every day without harming you because they're very long wavelength and low energy. See your little cell phone here? It's a little radio transmitter, and those radio waves pass right through your skull every day. You are irradiating with your skull with radio waves. But guess what? That's okay, because radio waves don't hurt you, contrary to popular belief. All right? On the other hand, as the wavelengths get shorter and shorter, the energy of the photons become higher and therefore more dangerous. Gamma rays, that's the kind of stuff that'll turn you into a teenage mutant ninja turtle. Okay? That will knock out the nucleotides in your DNA and cause usually bad mutations. I can take light and I can break light from various sources into various types of spectra. And when you did this in your lab the other day, I think I just threw away the sheet, but what were the different types of spectra that you guys saw when you looked at different types of light sources? In other words, not everything produces a rainbow when you break light apart. The person who first studied this was a Prussian scientist by the name of Gustav Kirchoff. I want to show you a picture of this guy here because he looks pretty serious. Check out this dude. This guy in the 1800s was one of the pioneering scientists to study the nature of matter and radiation. This creepy looking dude here was very much interested in why do some types of light sources produce rainbows, and why sometimes when I look at broken apart light, do I see those emission lines that we saw in our labs last week? And Gustav Kirchoff basically discovered that in general, there were kind of three different types of spectra that light emitting objects produce. Sometimes light emitting objects will produce pure rainbows. Sometimes they'll produce emission line spectra with those unique lines. And in certain cases, you can even get light to produce an absorption line spectra. He produced a set of laws known as Kirchoff's laws, and that's what we're going to tackle next. Okay, introducing Kirchoff's laws of radiation. And they're supposed to give you good judgment about how light emitting objects produce the various types of spectra. So the first law is called the law of black bodies. In physics, a black body is a term for an object that emits light after you heat it up. So a filament in a light bulb would be considered a black body. The sun is also considered a black body. And the law of black bodies goes that a hot, dense solid produces a continuous spectrum, where you guys will remember that continuous spectrum is code for the rainbow. Usually black bodies are light sources that produce pure white light, but not always. Okay, the second law is called the law of emission. And the law of emission states a hot, thin gas produces an emission line spectrum. You guys should be relatively familiar with the emission line spectrum. You saw me produce those in our lab session when I put those tubes of gas into the power supply. Now, I attempted to show you an absorption spectrum by showing you sunlight, but my spectroscope did not have high enough resolution, or my camera didn't. But sometimes you can produce the law of absorption. The law of absorption says a cold, thin gas in front of a black body produces an absorption line spectrum. I think I'm going to run out of room here. Produces an, let's see if I can do this. An absorption line spectrum. Sorry, my handwriting gets crappy as I get down to the bottom of the board there. Get that copied down. Now, I have a couple more modules to do here before we're ready for our homework. I'm going to try to make this quick. Let's talk about the difference between emission and absorption to see what you guys have already learned. I'm going to go to slide 12 here. Where is it? Okay. Let's see what the chat's saying. No, Kevin, the math, well, we aren't going to do the math behind Einstein's rings, but it's not as crazy as you think it is. All of these things are manageable if you take them in bite-sized chunks. Okay, I want to see what my students know here. Let's start by talking about this. What type of let me just ask some simple questions to make sure you're with me. What type of spectrum is this that I just circled? What type of spectrum is this? That's right, Emily. It's an emission line spectrum. Okay, what about in microscopic details? Why does a hot, thin gas produce emission? Where do these emission lines come from? Do you guys remember? What produces these emission lines? This one you might have to talk to me instead of typing.
It's the colors that a specific element reflects back out, and the rest is absorbed.
Not reflect. No, here at Arunsak, it's not about reflection and it's not about absorption. This is actually emission. The atoms are producing the light. And the question that I'm trying to get you to answer, Arunsak, maybe you could even try it again. What in particular is producing these individual photons? What produces the red line? What produces the blue line? What produces the purple line? Anyone? No? What if I gave you a hint? Kevin, that's not the right way to say it. You are correct in saying energy levels, and the energy levels are causing photons to be emitted. But it's not that they're hit with an electron. They're created when an electron drops from a high orbit to a low orbit inside the atom. The drop of the electron emits the photon. All right. Let's see if you can answer this question. What type of spectrum is this here? Is this an easy question or a hard question?
An absorption line spectrum.
Excellent. Now this might be, well, let's just see if you can guess how it works. Here you can see a rainbow of white light, but there are missing lines that perfectly correspond to the emission lines of hydrogen. Do you want to take a guess what causes these lines to be dark or black? How are these lines produced? Take a guess. No?
Is it because the electrons aren't dropping?
Yeah, so they must be doing what instead? Keep going with that.
They're just comfortable where they are. They don't want to go up or down.
The elements are absorbing them, Kevin. And whoever I was talking to there, it's not that they're comfortable. It works like this. Let's say I have an electron and the electron is in the ground state of hydrogen. Actually, let's go to my picture of hydrogen so that it's not quite as abstract as this. Hold on a second. When you produce an absorption line spectrum, you start off with an electron, which is in a low energy state, and it could be the ground state. Photons of all different wavelengths and energies are flying through this atom, and most of the photons just pass through the atom like transparent glass. But if you have a photon of exactly the right energy, and in the case of the 2-to-1 transition, I believe it's 120 nanometers or so, or actually maybe it's 96 nanometers, I can't remember. It's around 100 nanometers. If a photon of exactly the same energy as the jump comes into the atom, the electron in the lower energy state can absorb the photon and capture that energy and use the energy to jump up to the next higher orbit. It's basically the process of emission, but in reverse. Instead of an electron going from high orbit to low orbit and emitting a photon, now the electron goes from low orbit to high orbit and absorbs a photon. And that's why in this picture here, you can see the same lines seen in absorption that you can in emission. Just as the 2 to 1 transition produces a red line at 656 nanometers, if a red photon of 656 nanometers travels through your atom, the electrons will grab it and use it to jump from orbit 2 to orbit 3, causing a decrease in light at that particular wavelength. So both emission spectra and absorption spectra take place at the atomic scale. However, that's a little bit different than what happens when you're dealing with a black body, okay? And for our final notes today, I tried to give you a sense of what's going on with emission and absorption. I really want to zoom in on this law and teach you 2 new formulas. We're going to need them for our homework today. And our entire class, in a way, has been building up to this concept. A black body, the law of black bodies tells us that a hot, dense solid produces a continuous spectrum. So when I talk about a black body, I'm talking about a hot, dense, glowing thingy. Now, Kirchoff described it as a solid, but you are going to quickly learn that sometimes things that produce blackbody light are not solids, okay? So it's some kind of thing that is hot and dense and glowing. Black bodies produce, in general, kind of white light. And that white light, if you break it apart, is usually a solid rainbow. And there's one other thing that you really need to know about black bodies before you go forward here, and that's black bodies glow only because of their temperature, not because of their chemical composition. They glow due to temperature alone. And in other words, not chemical composition. I have a phrase that I like to associate with black bodies for students who are learning about them. The phrase goes like this: I glow because I'm hot. That's the concept behind a black body. I glow because I'm hot. Let's take a look at what I would think of as your everyday black body. Here you guys might want some examples. When I think of a black body, I think the perfect thing to think about is like maybe a steel ingot glowing in a forge. There's this one kind of crappy picture that I think sums it up right here. Let's see if I can, I grabbed this off the internet at some point. You know what? That's pretty good. That's actually a different one that I was looking for, but I'll take that one. Yeah, the hell with it. Oh, this is the one I really like too. So let's look at this picture right here. You guys can see a lump of metal, it's probably steel, and it's been heated up in some foundry. And this clump of metal is now emitting light. It's glowing because you've heated it up. And you guys know this happens if you've ever put some stuff into a fire. I was kind of like a little pyromaniac as a kid, so at one point I've tried to set just about everything that moved on fire. You know that if you put metal into a fire, it'll eventually warm and it will begin to glow. And another nice example of a black body, if I could go to my slides here. Where's this thing? Here's a great example. Let's take the poker that's in your grandparents' fireplace, okay? And so you've got an iron poker, and at room temperature, it's cold, so it is not glowing. Actually, that's kind of a lie, but I don't want to get into that. Okay, anyways, let's just tell you a lie, because lies are easier than the truth. And let's just say that when it's at room temperature, this iron poker is not glowing. As I put the iron poker into the fireplace, it begins to warm up and it glows. And you're going to notice that two things start to happen. First, it produces a kind of dull, weak orange light, and then the poker becomes red hot. And if you keep heating it up, it'll eventually glow white hot. That's usually about as hot as you can make it inside of a backyard fireplace. But if we were to bring this into a foundry where they have blast furnaces, which can heat up metals well beyond the temperature of a simple fireplace, as you continue to heat this metal up, you would eventually see it glow a kind of pale blue color, all right? There are two formulas associated with this behavior that I need to teach you before we can end class. Okay, as I heat a black body, you get two effects which are described by two different famous formulas. The first effect is that more temperature equals more light emitted, okay? And this effect is described by something called the Stephan-Boltzmann law. Get ready for this one. The Stephan-Boltzmann law tells you that the brightness emitted at the surface of a black body is a new constant of nature. This is the Greek letter sigma. Sigma times its temperature to the fourth power, where sigma is a new constant of nature known as the Stephan-Boltzmann constant. And it has a value of 6 times 10 to the minus 8 watts per meter squared per Kelvin to the fourth. Kind of a lot. Watts per meter squared per Kelvin to the fourth. This is a constant of nature. It's always the same. It's known as the Stephan-Boltzmann constant. The real meaning of this formula is that the temperature controls the quantity of light emitted by your black body. If you guys think of that ingot that you saw in the forge, you can think of this as being the number of watts per square meter that is glowing off of the surface of your black body, okay? So you've heated up your black body to some temperature, and that temperature will determine the amount of light that a square panel is emitting. The other effect that we see when we heat up a black body is not only do warmer objects produce more light, but that the color changes as well. And here's how I'm going to describe this. More temperature is going to equal bluer light. Or I'm pretty sure I just made up a word there called bluer, okay? And this is described by a famous formula known as Wien's law. Wien's law tells us that the peak wavelength or the maximum wavelength emitted by a black body, the peak color, is a random number, 3 million, divided by its temperature. And in order for the units to work, the units here are 3 million nanometers times kelvins, where I've put the units in purple so you won't confuse them with the formula. Taken together, these two formulas are very powerful tools that allow you to analyze the type of matter that is emitting light. You can measure the temperatures of stars. You can calculate what type of light is emitted by a light bulb. Okay. My hope was to do some sample problems on those two formulas, but it's 1 o'clock. And we're going to use them in our homeworks anyways. So I guess we'll just wait for homework time to do the sample problem. Sound good? Okay. You guys want to take a little tea break before we tackle that homework? Yep. Today's homework will not be as bad as some of the previous ones, okay? All right, so see you in, what do you want, 10 minutes, 15 minutes? 10? Okay. Okay, I'll see you guys in 10 minutes. Okay, welcome back, friends. I hope some of you will continue to share videos so I'm not just talking. Actually, Arunsak's with me, so Arunsak's my boy. We're gonna get down in this homework here and do it together. You all can just troll what goes on. Kevin Ryan has asked an interesting question in the chat. Okay, coffee is important, Christopher. So in fact, I could use a reheat of coffee myself. I want to address Kevin's question. He said, I thought 2.9 times 10 to the minus 3 meter kelvins is what I used in Science Olympiad. And you bet it was, Kevin. You'll notice that these units have been converted into nanometers. First of all, Kevin, hi, it's nice to finally see your face. 2.9 is approximately equal to 3. Do you agree with that statement?
Yes.
Okay. And your version of the formula was 10 to the minus 3, but you were using meters for Science Olympiad. I've cooked the books here so that your answer will come out in nanometers, which if you think about it, for wavelengths around visible light, nanometers are much more useful than meters. Remember that there are 1 billion nanometers in a meter. And what power of 10 is billion, Kevin?
To the 9.
9. So if you do 6 minus 9, what do you get? -3, right? So the only reason yours is different from mine is because mine's cooked so that it comes out in nanometers. Does that make sense?
Yeah. I had I was looking at it and I was like, oh, wow, that was I jumped the gun essentially.
No, that's okay. It's worth talking about. In fact, the version that we often learn, usually they do, what is it? Lambda max is, I think it's 0.29 over t. That's if you want it to come out in, I guess that must be micrometers. It doesn't matter. I've grown really used to this one because I like my answers to come out in nanometers. Usually, by the way, black bodies, in terms of stars, they tend to have Wien peaks that are somewhere between the infrared through the visible into the UV. So those are all great wavelengths to measure in nanometers. Okay, why don't we go ahead and tackle today's homework? That's the business that we're after here. So I'm going to erase all this nonsense. Oh my gosh, I'm choking. All right. Let's get our name on that paper. This is Astronomy 1020. Put your section down for good measure. I believe this is homework number 5. We have some problems from chapter 5 and some problems from chapter 6. Does anyone have the numbers in front of them? Or am I going to have to look that up too? Great.
I got you.
Oh, you got me? Okay. What?
55, 58, and 60 for chapter 5.
Okay.
And chapter 6 is 51 and 54.
Okay. Arunsak, do you want to read off chapter 5, 55 for me?
Yeah. Give me a second.
Sure thing. I should have given you the questions right there. Oh, I'm going to get a tissue.
Wait, what? Okay, you ready?
Yes.
All right, so the title is UV photon.
Okay.
What is the energy in joules of an ultraviolet photon with wavelength 120 nanometer? And what is the frequency?
All right. I'm stumped. How do I do it? I'm already lost.
We can use one of the equations that you put up earlier. One of the
Good
three.
idea. Arunsak, just for the benefit of everyone else, what kind of a quantity is this, 120 nanometers? What did they give us?
A length?
Not just a length, but a wavelength, right? In other words, I wanted to see if you understood that they gave you the variable lambda, wavelength, okay? But yes, wavelength is a length. All right, you didn't understand that? Well, I guess you do now. So what formula do we want then? Ooh, that's cool.
We want the C equals. We solve that for lambda.
Yeah,
So
what was the formula again?
It'll be lambda equals frequency over C.
Okay, so just so that everyone follows where you started, he started with this formula and he's solving for frequency by flipping the wavelength down. So it's C divided by wavelength. What is C?
Isn't it Planck's constant?
No, it's the speed of light. Planck's constant is h.
Okay. Now I gotta go find that. Hold on.
I should give you guys the formula sheet that we're going to be using in the exam. How many weeks to the exam? Just 2, right? Have you guys thought about that? Have you thought about how totally screwed you are? Let's see. Dropbox. From now on, guys, I want to start training you to use your formula sheets. AS1020 midterm formula sheet. Did you guys get that in the chat log? Why don't you open that up? Arunsak, that'll help you. Yeah. So you can see the speed of light on the second line of that formula sheet. What is it?
It's 3 times 10 to the 8 meters per second.
And what's the wavelength?
The wavelength is 120 nanometers. Would it be 250 times 10 to the 4?
Nope.
No, I did it wrong.
I think, aren't the units off?
Yeah, Christopher. I was just going to keep playing it out until one of you figured it out. And I even thought about just letting you get the wrong answer because I'm crazy like that. Christopher doesn't like what was happening there. Christopher, can you explain what the beef is?
We're using nanometers instead of meters.
Right, these
Like-
two have to be the same units, don't they? That means we have to do a mini game, a Arunsak, atone for your sins. Help me convert nanometers into meters. How do I do it?
Yeah, so start with 120 nanometers.
Correct?
X bar. Nanos on the bottom. Meters up top.
You might even be able to find the conversion in that sheet. Or unless you know the conversion by heart.
So it's 1 meter up top,
Uh-huh.
and then it's, let me see, 1 times 10 to the negative 9.
So 1 meter is equal to a billionth of a nanometer. Right? This meter here is a billionth of a nanometer.
I gotta write this all down. Can you pick on someone else for now?
Oh, fine. Hey, Christopher, how do you feel about this?
Eh?
Oh. How's Mr. Science Olympiad feel about this? Yeah, eating a burrito. Kevin, wait, come back to me, Kevin. You cool? Is this cool with you?
What? No.
Yeah. Do you think this meter is equal to a billionth of a nanometer? Does that sound right to you?
No.
No, not at all. A Arunsak is made of very
lump.
say that again,
Did
Kevin?
I'm supposed to put the 1 times 10 to the 9 at the top.
The -9 on top. That's right.
Negative.
Because remember, on the formula sheet, it says 1 nanometer is equal to a billionth of a meter. But what Arunsak did here is actually kind of important. This is a mistake that many people are going to make on the exam. And I'm trying to show it to you now. You've got to keep the numbers with their units. He has mixed the numbers and the units. So we want 1 nanometer is a billionth of a meter. All right, what's that equal to? Come on, guys. Let me tell you why it's not my job to punch this. Because I've already done this 100 times. That's why I have my college degree. That's why I have a job. I now earn money using my brain. Okay. Yes, Tiffany, you could say 1.2 times 10 to the -7. Tiffany, if you punch it into your calculator, you'll certainly get that. But rather than write that, Tiffany, you know what? I've got a different idea. This is fine if you want, Tiff, but you know how I would have done it? I would have just done 120 times 1, and I would have just written it as 120 times 10 to the -9. That's an even faster way to do it, okay? But Tiffany, your answer and my answer are the same answer. It's just that my answer is cooler than yours, okay? That's all. That's the only difference, really. So let's plug in my answer because it's cooler. 120 times 10 to the -9 meters, okay? And now you punch it up. It's just a point of style, Tiffany, that's all. Make sure you have that conversion in your answer because I want to see it. I just needed my board back. Okay, what do you get when you plug them in? Caitlin, are you not plugging? Are you just plugging up your nose, or are you punching as well? Okay, Emily. Yes, Christopher, sounds good. Emily, can you just read out what's my answer be?
(2.5 times 10 to the 15th).
What are my units? Yes, Reardon.
Is it seconds?
I'm sorry?
Is it seconds?
It's not exactly seconds. I agree that meters cancels out, but that does not leave you with seconds. It leaves you with something else. Does anyone understand me? That's right, Reardon, and whoever else typed it first. It leaves you with per seconds. Emily, it's important for you to realize that seconds on the bottom is not the same as seconds on the top. They're totally different units, okay? You were just stopping at, well, there's an S left over, so I'm gonna call it seconds. But you've neglected your duty to remind us that it's on the bottom of a fraction bar, not on the top. And a per second is also known as what, students? What do we call per seconds?
Hertz.
Hertz. All right, we also have to find the energy. Guys, we're moving kind of slow here. At this rate, we're gonna be here for 3 hours. So you guys have to step on, put a little juice in your caboose, okay? How are we gonna get the energy? What formula?
Say E equals Planck's constant times frequency.
I like it. Planck's constant is 7 times 10 to the minus 34 joule seconds. And the frequency is 2.5 times 10 to the 15 per seconds. Punch them up. (1.75 times 10 to the negative 19. Did I get that right? 1.75 times 10 to the minus 19?
I got to the minus 18.
Oh, okay. I screwed up. But is it 1.75?
Yeah.
How did I do that in my head? Yes. Not joules per second, Reardon. Wrong units. What are the units?
Joules.
Yeah. Just joules. So I tried to do it in my head. Thanks, Cameron. And what I did is, in my head, I went 7 times 2.5 is 14, 15, 16, 17.5. And then I did negative 34 plus 15 to get negative 19. But I forgot that when I moved it to 1.75, that changes it to minus 18. So I tried to do it in my head, but I made an error. Okay, that's number 55 down the hatch. Copy it all up because we got to move on. I'm going to erase now. Christopher, could you read number 58 for me?
Gotta pull it up. All right.
Bless you.
Thank you. Thank you, thank you.
Thermal radiation laws. Part A. Find the emitted power per square meter and wavelength of peak intensity for a 3000 Kelvin object that emits thermal radiation.
Okay, so we're going to be using our two formulas here. When they say the power per square meter, they mean the watts per square meter. Do you guys remember what that quantity is called? What quantity do we measure in watts per square meter? I really didn't like the way the book phrased that question. It's kind of like saying, how many dollars is that apple? It's just an awkward way to speak, you know? How many dollars is that?
The brightness.
That's what they really asked us for. They want to find the brightness and they want to find the peak wavelength of a hot glowing thingy with a temperature of 3000 Kelvin. By the way, 3000 Kelvin is close to the temperature that this filament in this light bulb is raised to when it shines light. Okay, so what are our formulas, Christopher? What am I going to do? Let's start with the brightness. Which formula do I want?
Oh, goodness. 1 second.
Do you have that from today's lecture?
I have, like, I think the conversion factor, the energy over time thing, the inverse square laws. I'm not sure which one.
By the way, thermal radiation is code for black body. Does that help you? A thermal radiator is a black body.
Would we be using the Stephan Boltzmann law?
Exactly. For the first part, anyway. Which says that the brightness is sigma times T to the fourth. Sigma is a constant of nature, the Stephan Boltzmann constant. 6 times 10 to the minus 8 watts per meter squared per Kelvin to the fourth times 3000 Kelvin raised to the fourth power. I'm betting a lot of you do not know how to take a fourth power. So let's just practice, okay? 2 to the power of 4 is 16. To raise to a power, I'm going to use this button here, the X to the Y key. Let's try raising 2 to the power of 4. 2 to the power of 4 is 16. Make sure you can do that. All right, let's try this guy now, okay? So we'll do 6 exp minus 8 times 3000 raised to the power of 4 equals. What's my answer? 2 sig figs.
Looks like 4 4.9
4.9
million times
Million.
10 to the 6.
And can you tell me the units, Christopher, since you're doing so darn good?
Give me a minute. Does Kelvin cancel?
That's right, because here's Kelvin to the 4th power, and that Kelvin is also raised to the 4th power. Leaving us with what, Christopher?
Like watts per meter squared?
And that makes sense because this is a brightness. Box that up. Ah. Okay, what about the peak wavelength? What formula should I do there, Christopher?
That would be Wien's law.
Yeah. It looks like Wien's law, but the Germans call it Wien's law, right? Because that's how they pronounce the W's. So lambda max is equal to 3 million nanometer kelvins divided by 3,000 Kelvin. I don't even need a damn calculator for that. Maybe you guys do.
That would be 3,000, right?
3 divided by 3 is 1, Christopher. So try again.
1,000, yeah.
1,000. And the units, you said it? 1,000 what? Yes, Tiffany.
Nanometers?
Yeah, nanometers. You need units. I want you guys to know that during a test, okay, I have been known to just put the same answer 5 times. Like A is 1,000, B is 1,000, C is 1,000, D is 1,000, E is 1,000. But each time I put a different unit. Nanometers, micrometers, millimeters, centimeters. So sometimes it's more about the units than it is the number. You should also be prepared for this question during an exam. And I wonder how many of you could answer this right now. In what regime of the electromagnetic spectrum is light with a wavelength of 1,000 nanometers found? 1,000 nanometers is which zone of the electromagnetic spectrum? Who can answer that question?
Radio?
Nope.
Infrared.
Yeah, how did you know it was infrared, Christopher? Remember that red light tops out at 700. So 1,000 nanometers is right here at the, they call this the near infrared. Let's write that down. Okay, now we got to do part B. I'm going to race. I'm racing. How about part B, Chris?
Find the emitted power per square meter and wavelength of peak intensity for a 50,000 Kelvin object that emits thermal radiation.
Okay, let's do this faster. Brightness is sigma t to the 4th. Sigma is 6 times 10 to the minus 8 watts per meter squared per Kelvin to the 4th times 50,000 Kelvin to the 4th power. Punch them up.
Three 3.75 times 10 to the 11 the watts per meter squared.
Nice. Christopher, if it's okay with you, I just rounded up to 3.8. Just because, the hell with it, right? Okay, how about the peak wavelength? That should be pretty easy.
That would be 60 nanometers.
Christopher, since you were good at this before, can you tell me what regime of the electromagnetic spectrum 60 nanometer light is found in?
I would guess either gamma rays or something close to it. UV.
It's UV, yeah. It may not be obvious to you guys, but this is related to the fact that stars come in one of 3 colors. Stars are usually either red or white or blue. And the red, white, and blue of the color of stars, it has to do with their black body spectra. A black body emits light at all wavelengths, but there's always some peak wavelength that it emits more than others. Stars tend to have a range of 3,000 Kelvin at the coolest stars, all the way up to maybe 50,000 Kelvin for the hottest stars. You can see that the peak wavelength goes from the infrared towards the UV as you get warmer and warmer. Red stars tend to have peaks which are at the red end of the spectrum, or maybe even in the infrared, and they pump out a lot more red light than blue light. Stars like the sun peak in the middle of the visible spectrum, so they tend to look kind of whitish or yellowish. And then really hot stars have peaks that are in the ultraviolet, so they give off a lot more blue light. So because star temperatures range from 3,000 Kelvin to maybe 30,000 Kelvin, stars tend to either be reddish, whitish, or bluish. Okay. Caitlin, are you up to reading a problem? No, you're sicky? Okay, Emily, you down to read for me? Well, I'm glad you're here with us anyways, Caitlin. We don't want to miss too many lectures. Emily, are you cool with reading? I don't have too many people sharing video with me today, so I gotta make use of what I got.
Let me just pull it up real quick.
All right.
60, taking the sun's temperature.
Chapter.
The sun radiates.
Sorry, let me just catch up to you if you don't mind. Okay, go for it.
Okay. Taking the sun's temperature, the sun radiates a total power of 4 times 10 to the 26 watts into space. The sun's radius is about 7 times 10 to the 8th meters. A, calculate the average power radiated by each square meter of the sun's surface. Hint, the formula for the surface area of a sphere equals A equals 4 pi r squared.
With an assist from the birds, okay? I don't know about you guys, but This sounds very much like something that we learned about in today's class. What the shit does power per square meter mean anyways? Sometimes you got to know how to translate these guys. They speak in funny ways. What the hell does power per square meter mean? I think Christopher had figured this out earlier. I don't know if he remembers. Or Runsack, do you know?
It'd be a unit of force, but nothing comes to mind.
I apologize, but it's not a unit of force. Power, what are the units of power? Watts, Cameron says. So power per square meter actually means watts per square meter. What quantity has units of watts per square meter?
Joules?
Sorry?
Is it
Joules, Cameron, are another unit. I'm not asking you for a unit. I'm saying the units are watts per square meter. I want to know what the quantity is.
Brightness.
That's right. You see, Christopher, what they really... Oh, okay. Are there two Camerons? It doesn't matter. Anyways, they should have just said, please calculate the brightness, but instead they had to say it like a jerk. Power per square meter. That's the same as brightness. Now, can you guys think of a formula that might let us calculate the brightness at the surface of the sun? So the sun is a ball of radiating light. It's got a radius r. And we're trying to calculate the brightness at the surface of the star. What would be a good formula for that?
Brightness equals the L divided by 4 pi r squared.
Excellent. Where we're going to use the luminosity of the sun and the radius of the sun. So I put in the little sun symbol. Our units are already good because they were kind enough to give us the sun's radius in meters. That means we don't have to do any dimensional analysis mini game here. We can just plug and chug. So let's set it up. Okay, let's see if you guys can do better this time than you did during the lecture. Caitlin, even if you're sick, I want you to be punching into your calculator, okay?
I'm just finished writing it down.
Okay, sure. I know it's hard to concentrate when you're sick, but the calculator training is invaluable. Sure, Arunsak, you got it right, but now we'll have to figure out how to say that. You want to give it a whack, Arunsak?
I gotta count the digits first. Give me a second.
Yep. I need some coffee. I'm dying. Caffeine levels are being restored. What did we decide our final answer was?
Got 6 times 10 to the 7
I'm
watts
sorry,
over
you
meters.
kind of glitched out there. One more time.
6 times 10 to the 7.
Let's keep 2 sig figs, and then let's move the decimal point back once to get it in terms of a million.
Okay. 6.5.
Let's do 65 instead.
Okay.
You'll see why. What's my power of 10 if you slide the decimal place to the 5 instead of the 6?
6.
Be 8.
6.
6.
Do I still have that? Look. So Arunsak, 1, 2, 3, 4, 5, 6. I like to think of it as 65 million watts per meter squared. .5 times 10 to the 7 would have been correct, Arunsak. There would have been nothing wrong with that. But I think it's cooler to remember this as 65 million watts per square meter. That's the answer to part A. Damn, that coffee's good. Okay. I'm erasing. We have to get to part B. Okay, buddy, let her rip.
Are you asking me to read?
Were you, oh, I'm sorry, Emily, you were reading, right? Sorry.
1 second. Using your answer from part A and the Stephan Boltzmann law, calculate the average surface temperature of the sun. Note the temperature calculated this way is called the sun's effective temperature.
There's a point to this problem. I know that the temperature at the surface of the sun, well, it's the number you're about to get, but you don't take the temperature of the sun by flying out to the sun and dipping your thermometer into the photosphere. That doesn't work. The way we get the temperature of the sun is by studying the amount of light that it emits. And we use the Stephan Boltzmann law to do this. Now, let's imagine that we have the Stephan Boltzmann law. We know that the brightness at the surface of the sun is due to its temperature alone. But we have the brightness of the sun from other means. We can solve this equation for T, and let's see how we would do that. First, I would divide both sides by sigma, the Stephan Boltzmann constant. And I would get brightness over sigma is temperature to the 4th. Do you guys know how you get rid of a 4th power?
Fourth root.
That's right. So we get that the temperature is the 4th root of brightness over sigma. And this is a pretty important formula here. It's how we take the temperature of stars, one of the ways. It's called the effective temperature. We have the brightness and we have Stephan Boltzmann's constant. So we'll plug it in for this equation. And we get the 4th power of 65 million watts per square meter divided by, actually this time, I think I want to use the full Stephan Boltzmann constant. Oops. Yeah. The actual value, up to now I've used 6 times 10 to the minus 8, but here we're going to use 5.7 times 10 to the minus 8 watts per meter squared per Kelvin to the 4th. I think the Stephan Boltzmann constant is 5.7. Let's just check that, shall we? I usually just say 6 because I'm lazy and I don't care, but today I actually care. Stephan Boltzmann constant. Let's see what Google gives us. Yeah, 5.7 times 10 to the minus 8. Okay, guys, what do you get if you plug that in? Two sig figs will suffice. Oh, you guys probably don't know how to take a 4th root. Is that what's going on? I forget that I have to teach you that. Okay. Here. Okay, can we all? Hey, Arunsak, what is the 4th root of 16?
Is it 2?
Right. And let me tell you about what a 4th root means, Arunsak. The 4th root of x is another way of saying x to the power of 1/4. So your calculator, instead of having a 4th root key, right above this, I'm gonna have to adjust the focus for you guys to, that means I gotta call up the damn Logitech thing. Yeah. Hold on. 4th roots tend to wig people out, so I'm gonna do this right. I just gotta get this. I have to have access to my camera here. Okay, so let's go to 30 or so. Okay. Rather than having a 4th root key, you have an arbitrary root key right there. It's x to the power of 1/y. So Arunsak, let's see how we would do the 4th root of 16. First, we would type 16. Then we would hit shift. We would hit arbitrary root 4. And then we'd hit equals. Make sure you can do that, okay? Now, let's try this one. We're going to do 65 exp6. We're going to divide it by 5.7 exp -8. First, we hit equals, and then we're going to take the 4th root of this number. Shift arbitrary root 4 equals. What do you get? Emily, yes. Caitlin, yes. Arunsak, yes. Christopher, hold it a little closer, buddy. Christopher. Tiffany, yes. Christopher, yes. Okay. You all do me proud. How should I round it? What should I put as my final answer?
$58,000 Kelvin, or
Not
no, 5,800 Kelvin.
Yeah. You could say 5,800 if you wanted to.
I think that was what I was trying to say.
Yep. And that's the legendary surface temperature of the sun, 5,800 Kelvin. That's a number I'm going to want you to accidentally memorize over time. All right. We've gotten 3 problems down. We're making good time. I'm going to erase this, okay? We're going to need to learn 2 new formulas from chapter 6. And this is actually just a little bit ahead of where we are in lecture. But luckily, you guys have already sort of seen versions of, or a version of the first formula. For chapter 6, number 51, we're going to use a formula that I refer to as the small angle formula part 2. And the idea is that sometimes you have 2 binary stars and you want to look at them from some distance away on Earth. The separation between the stars is S. The distance between the 2 stars and the observer is little d. You guys will remember that in chapter 2, we called the angle theta, where theta was measured in degrees. But I even hinted to you guys at the time that degrees were a really crappy unit to use because normally stars are separated by really, really tiny angles. I'm going to want to introduce a new version of the small angle formula where we don't measure the angle in degrees, but instead we measure the angle in arc seconds. And to remind the viewer that our formula is now going to be in arc seconds, it's going to be helpful to change the variable to the Greek letter alpha. Alpha is the angular size or the angular separation of the object in arc seconds. And in the interest of time, if you do the conversion factors, you get a formula that looks like this. The separation between the stars is the angular separation in arc seconds times the distance divided by the legendary number 206,265 arc seconds. I call this the small angle formula part 2. It's the same as the small angle formula part 1, but now here's the key idea. Alpha is in arc seconds instead of degrees. I know you've already read for us, Arunsak, but would you be willing to do it again? Because I don't have many actual humans interfacing with me right now. Oh, Tiffany, Tiffany, you want to read a problem? We'd like
Okay,
to.
awesome.
Okay, yeah. Tiffany, I want to hear your voice.
Okay, 51, right?
Yes, please. From chapter 6.
Okay, it says closed binary system.
Okay.
And then it says, suppose that 2 stars in a binary star system are separated by a distance of 100 million kilometers and are located at a distance of 100 light years from Earth. What is the angular separation of the 2 stars? Give your answer in both degrees and arc seconds. Can the Hubble space...
Keep going.
Can the Hubble Space Telescope resolve the 2 stars?
I'm going to give you guys a boost here. It asks for the angle both in arc seconds and in degrees. Screw degrees. We don't need the angle in degrees. That's a total waste of time. We're going to have to rearrange this formula, however, to solve for alpha. And algebra, you flip the letters around, and you get this formula for angular separation. Alpha is 206,265 arc seconds times S divided by D. This is also the small angle formula, but this is the small angle formula solved for angular separation. Tiffany or anyone else in the class, I need you to identify in this problem, what is the S, what's the S, and what's the D in this problem?
The S is 100 million kilometers.
Correct?
D is 100 light years.
Can I divide light years by, or can I divide kilometers by light years, Christopher?
No.
Okay. Tiffany, since I don't get to interface with you as often as I'd like, and you made the mistake of sharing your video with me, which you're soon about to regret, okay? Would you be kind enough to help me convert? This is training just for you. You're getting personalized attention, Tiffany. Could you help me convert light years into kilometers using the tool called dimensional analysis? And I'll give you a hint. Did you get the formula sheet that I gave you?
Yes, I did.
If you look on the formula sheet, Tiffany, where is it? You'll find the conversion from light years to kilometers right there, okay?
Okay.
Okay, so why don't you walk through this nice and slow? You can use the, if you don't know what to do, we can read the 4 steps of dimensional analysis. But if you think you know what to do, just tell me.
I don't think I know what to do.
Then, well, then that's a good thing that we're trying this together, okay? So do you have your notebook handy?
Yes.
Do you have the notes from the first class where we have the 4 steps of dimensional analysis? If you
I
just
believe
read them
so.
back with me, we'll be able to work this out together.
Let me see.
Look for the 3 stars. In your class, I believe I had you put 3 stars next to the 4 steps of dimensional analysis.
Yes, I found it.
You found it. Okay. So let's read out the numbers together, or read out the steps together. What does the first step say, Tiffany?
It says write down the numbers to
Convert.
convert with the units.
Okay, so what
Yes,
number should I write down, Tiffany?
The 100 light years away.
Good. Okay, and then what's step 2?
Multiply by a division bar.
Okay, what's step 3?
Put units in the first to cancel.
This is the big moment for you. I need some units on top and some units on bottom. What are you going to do?
So the 9.5.
No numbers. The whole.
Oh yeah, sorry.
Yeah.
The km at the top and then light years in the bottom.
Correct. All right. What's step 4?
Put the numbers in second using conversion factors.
All right. Now I showed you where to get that conversion factor. It's right here. It's right here.
Mm-hmm.
Your job is to put the numbers into the right slots. Okay. So what number on top? What number on bottom?
1 at the bottom.
Yep.
And then it was right here. 9.5 times 10 to the 12.
I bet you could do this without a calculator. That's 12 zeros. How many zeros do you have here?
2.
So what should my end answer be?
Well, should it be? Yeah.
It's still 9.5, but what's the power?
To 14?
That's right. You're so good, Tiffany, you don't even need a calculator. That's pretty impressive, okay? All right, so we've now converted our distance into kilometers. Unfortunately, I'm running out of board space, so I might have to erase that. So Tiffany, take a moment to write that down. Everyone take a moment. I want to see that in your answer, okay? I kind of squished it into the side there. We're getting there, guys. We're getting there. We haven't even spent an hour yet. We're doing good. See what's happening in the chat log. Oh. Okay, I'm going to erase that conversion. Make sure you have that number down. Here we go. Okay, so let's plug it in. We have 206,265 arc seconds. Christopher has pointed out that the S is 100 million kilometers. That's the separation between the stars. And Tiffany helped us work out that the distance is 9.5 times 10 to the 14 kilometers. Punch them up. Looks good, Christopher. Why don't you shout at me? 1 sig fig is fine.
Point 02
Units?
that'd be arc seconds.
Good. I'm going to write it this way, Christopher. 0.02 arc seconds. Always put your leading 0 out front. That's a classy move. Tiffany, that's part of the answer to this problem. But if you can go back to the reading again, they asked us to do something about the Hubble, and I think we need to be reminded about that.
It says, can the Hubble Space Telescope resolve the two stars?
Okay. Can Hubble resolve the two stars? Now, what they tell us in the reading of the textbook is that the so-called diffraction limit, the diffraction limit is how tiny an angle can my telescope see. The diffraction limit of Hubble is 0.05 arc seconds. Class, can Hubble resolve the two stars if its limit of resolution is 0.05 arc seconds? Oh, Caitlin says no. Very good. Why not, Caitlin? Are you too far? Oh.
Sorry, it's because 0.02 is too small of a resolution for it.
Excellent. Now I'm going to ask you a slight challenge question. What would it look like if Hubble tried to look at these binary stars anyways? What would it see in its field of view if it can't resolve the two stars? It will still see something. See, it's not that the stars are too dim. It's that the angle between the two stars is too small. So can you or can anyone imagine what that would look like?
They want to like guess it'd look almost like two cells mitosis.
Yeah, kind of. Cameron said it the best of all of you. He said it's just going to look like one star because the two stars will be on top of each other. But Christopher, I actually really like what you said too. Can I explain why Christopher talked about two cells in mitosis? I have a nice slide. You know, learning about astronomy, one of the things you're supposed to learn is what is the difference between a resolved object and an unresolved object. And I hope to God I have a picture of that somewhere. I think I do. Here we go. Slide 131. Caitlin, if Hubble could see less than 0.02, it would see the two stars the way that you see on the right. Star 1 and star 2 would be separated by some tiny angle. But here's Christopher's cool point about the cell mitosis. As the stars get closer and closer together, first they'll kind of merge into a peanut shape, and that's what you were thinking about, right, Christopher? Was that? Yeah. But eventually, as your resolution gets suckier and suckier, the two stars would just merge into a single star, okay? So you guys did great. Let's add a statement there to that, okay? So let's say what Caitlin said, no, Hubble cannot resolve the two stars as its diffraction limit 0.05 arc seconds is greater than 0.02 arc seconds. And underline diffraction limit, because this is you learning that diffraction is what causes that limitation. Okay, 51 down. I'm going to erase. Are you okay with that, Arunsak? Arunsak, now that I've gotten Tiffany to read, will you read the final one for us? I'm going to erase here.
Sure. 64.
Chapter 654.
Yep. Title is The Size of Radio Telescopes. You ready?
Almost. Hey, actually, Arunsak, before you read it, let's all take a moment to do some Bob Ross together. Let's draw a little basic radio telescope, okay? So here's how we draw a radio telescope. First, we'll have some support struts. And then make a big radio dish. So usually a radio telescope has a big giant dish, and then it has something called a feed horn. And the feed horn are like these two little structures that stick out, and there's this detector that detects the radio waves. Okay? So that picture is a sucky picture. Let me show you what a real
Isn't there like a really big one in like either Cuba or Puerto Rico that's like built into the ground?
Yeah, that's called the Arecibo radio telescope. It's so big, and I wanted to talk about it, that they built it into a karst depression, which is a type of mountain valley. They call it a karst. And so the radar dish is actually built into the ground. It was one of the biggest ones in the world. That's their feed horn antenna. Probably you should start off by looking at a different one, like the Effelsberg radio telescope. This is a 100-meter radio telescope. And let's see if we have a nice, yeah, here's a nice picture. This is one that's in Germany. It's another legendary radio telescope. And if you're going to start learning about radio telescopes eventually, then this is a great example. So here you can see the dish. This captures the radio waves. And the radio waves are all brought to a focus right there at the feed horn. So that's kind of what I was trying to draw. But my artistic skills are, well, they're not very good. Okay, so Arunsak, now that we've got a picture of what we're talking about, now you can read the givens and stuff.
Okay. So what is the diffraction limit of a 100-meter radio telescope observing radio waves with a wavelength of 21 centimeters? Compare this to the diffraction limit of the Hubble Space Telescope for visible light. Use your results to explain why. To be useful, radio telescopes must be larger than optical telescopes.
Right. You can actually do a lot with a crappy piece of shit optical telescope like this one here. The diameter of this telescope, I bet it's freaking 3 inches or something. Where's my rulers? Yeah, it's barely even. It's 2 inches. Okay, so you can't really see that there, but it's basically 2 inches in diameter. By comparison, the radio telescopes that you just saw on the internet were 100 meters. I forget what the Arecibo one was, Christopher, but Do you guys, well, I'll tell you about the newest big telescope in just a moment, but the Arecibo telescope has a diameter of 1,000 feet or 300 meters. So that's pretty wild, okay? The radio waves tend to be much longer wavelength than visible light. The typical wavelength, what do they say, 21 centimeters? But you might naively think that the radio waves are longer, so you need a bigger dish, but that would be too simple a way to put this. There's a property associated with light called diffraction. And diffraction tends to distort the image of a star. In that picture that I had up a moment ago here, do you guys see how these stars have like little rings around them? Those little rings are distortion called diffraction. And even the disk itself is kind of smeared out due to diffraction. Diffraction causes the two stars to kind of merge together in what Christopher called a cell mitosis shape. And the diffraction is what sets the limit on how small an angle you can see. So let me introduce something called the diffraction limit. And just to put it simply for now, the diffraction limit is how tiny an angle can I see? Or by I mean how tiny an angle can my telescope see? And the diffraction limit goes like this. The minimum angle resolvable is 2.5 times 10 to the 5 arc seconds times the wavelength of observation divided by d, where d is the diameter of your telescope dish. In an optical telescope, it would be the diameter of your lens. Because I want my angle to come out in arc seconds, it is essential that lambda and d have the same units. And let me just give you a hint, class. Here they are not the same units. Emily, I need your help. Can you help me convert the wavelength into meters?
So it'd be like lambda equals.
No. Just take this and convert it into meters using dimensional analysis.
Oh, 21 centimeters times 1 meter on the top, I think.
Could we do the units before we do the numbers?
Meters on the top and centimeters on the bottom.
All right.
And then 1 meter, I
Uh-huh.
think. And 100 centimeters.
Oh, fuck. Damn it. Ah! Sorry, I just had a seltzer catastrophe here. No food or drink allowed in the classroom. Oh, shit. At least it was only seltzer, I guess. All right. Sorry about that, guys. What did you get, Emily? That was silly.
0.21 meters.
0.21 meters. Okay, let's plug it into our diffraction limit then, okay? I'm gonna just erase this and make use of that. So it's 0.21 meters divided by 100 meters. Christopher, just read it to me. 2 sig figs.
520 arc seconds.
Isn't it 525?
Oh, 530
That's
arc
right.
seconds.
Hey, Christopher, usually you're pretty good on your toes here. Can you tell me how many arc minutes that is? What's the conversion from arc minutes to arc seconds?
60 arc seconds for 1 arc minute.
So divide that by 60, what do you get?
Minutes. Or 9 arc.
Even 9, right? That's about 9 arc minutes. How many?
The video's being weird again.
My video is?
You're frozen.
Yeah, it's frozen.
I'm sorry, guys. The internet just can't handle me today, you know? 9 arc minutes is like 1/3 of a degree.
It's still frozen, so.
I wonder if that's... He gone. I didn't dip. I would never dip. It's still recording. Okay. Damn it. Guys, I'm almost done. If you can put up with this crapola for just another minute or two. I wonder how many other people I lost here. I got the core crew anyways. As long as I got the core crew here. Oh, there's only... Wait. Oh, wait, hold on. I see what's going on. It's because I had the Logitech open. Hold on, I'm back. Here I am. Okay, I would never troll you guys. Yay. Okay, you're all back. I'm sorry about that. We're almost done too. We're so close to the end. Okay, let me just like speed up my point, okay? Because I'm sure everyone would like to just get to it here. If you have an angular resolution of 9 minutes of arc or 1/3 of a degree, I'm sorry, that's not even 1/3 of a degree. That's, let's see. 9 minutes of arc is 9/60ths. That's like 1/6 of a degree, right? Students, the angular size of the moon is 30 arc minutes or 1/2 a degree. If you tried to look at the moon through a radio telescope, it would only be 3 pixels across. That's how sucky a radio telescope is. This is what the moon would look like through a radio telescope. Instead of seeing like all the craters and stuff, the moon would be 3 pixels tall and 3 pixels wide. That's what the moon looks like through a radio telescope. In other words, this angle is wicked sucky. Minecraft moon, I like it, yes. It's a Minecraft moon. So why do you think radio telescopes need to be so big? What does that Minecraft moon have to do with why radio telescopes would be designed so large?
Because they're looking for quantity and not quality. They're trying to catch all of the waves, but not catch them accurately. No?
That's a good guess, but no. The quantity that you're talking about is called brightness. The moon is plenty bright. We'll get plenty of light from it. And usually with a radio telescope, you look at bright radio sources like the sun or like the center of the galaxy or the Crab Nebula or something. The answer has to do with the formula, Arunsak. Let's look at how the formula for the diffraction limit works. Can I erase this part of the answer? Because I need some board space here. Arunsak, the minimum angle is proportional to the wavelength divided by the diameter, right? But the wavelengths of radio telescopes are big. And as you know, if this number gets bigger and bigger and bigger, the minimum angle that you can see also gets bigger. If your minimum angle gets bigger, your image gets suckier and more Minecrafty. All right? But if I increase the diameter of the telescope, what will happen to your minimum angle, Arunsak, according to algebra or fractions?
You'll get a more quality image.
It'll get smaller angles, right? And that'll be like a better resolution. You want your pixels to be as tiny an angle as possible, right? For this reason, radio telescopes, they try to make them really big, but even still, back in the day, radio images of galaxies, like let's look at a 21 centimeter map of a galaxy. When I was a student, radio telescopes took these really sucky and kind of blocky images of galaxies. So here's two images of a galaxy. The first is seen in a photo negative, so it's reversed black and white, and you can see the galaxy as spiral arms. And this is what old school radio telescope images of galaxies look like. They were kind of pixelated and blocky. You could tell there was a spiral galaxy there, but the images were just of shitty quality. Why did we put up with them? Because there's things that you can see with radio waves that you can't see with any other type of light. For instance, radio waves at 21 centimeters allow you to see cold hydrogen gas. I'll be teaching you more about this as we go along. For now, here's what we should add to our answer. We should say radio telescopes operate at long wavelengths which lead to large diffraction limit angles and thus poor resolution. So now that's basically saying the minimum angle you can see is proportional to the wavelength. Now we'll talk about how by increasing the diameter of the telescope, you can decrease the angle. We'll say by making the diameter of the radio telescope big, by increasing the diameter of the telescope, you lower the diffraction limit minimize the angle. That's a little bit redundant, but I want to be. And improve and thus improve image quality. I've said that more elegantly in the past, but that gets the job done. I'm never teaching a lecture without iced tea again. It was total chaos, okay? How are we feeling? We got all that down? Are you not done yet? Okay. Take a second. No, Elijah, this is done. You're cool. Make sure you submit it. Peace out. Man, Elijah, I bet back-to-back lectures are probably pretty intense, huh? Anyways, you got stuff to do, so I'll see you later. Did you get all that, Arunsak? Nightmare. Oh gosh, you too? I'm impressed with you guys. You really pack a lot into a day. And I promise you at some point when you've got your degree and you've got the jobs you want, it will get better, okay? But you have to suffer a little bit while you're going through this. I had to do it too. Yeah, good luck, man. Okay, so why don't I get you guys out of here as soon as possible? I'm glad our homework's done for the day. Please submit those as soon as possible. Do not forget. Make sure you submit in a format I can read, like a JPEG or a PDF. Don't send me a .mov file or something. Caitlin's already on it, and you guys should be too. Photo, submit, like, comment, subscribe. Okay, any other questions for me before we end class today? No? Okay. Good luck, Arunsak. Good luck, Elijah, and take care, guys. Bye.